Hello, this video is finding this volume of the solid of revolution using the shell method as an alternative to what we've learned with the disc and washer method. This is called the shell method because it uses cylindrical shells, which I'm going to give you a better image of here than what you see out of this book in just a moment, and talk briefly about how the formulas come about here. The delta y being your thickness here, and this is a horizontal axis of revolution, and then delta x being the thickness of the edge of this shell for a vertical axis of revolution. Now, one thing I want to point out right off the bat here that's completely different from the disc washer method is that with the shell method, when you're doing a horizontal axis of revolution, you are integrating with respect to y, which is the opposite of the disc washer method, which was respect to x. And the same thing here is being the opposite. When you're using the shell method for a vertical axis of revolution, going around the y-axis, for example, you are using variable x to accomplish that, where that must be variable y in the disc washer method. So what we've got basically, and I'm going to show you another picture in a second here, is you're filling a region like this as it revolves all the way around with a bunch of just small shells. You can think of them as being circles in a sense because they're going to they're different shapes, they're different thickness as you cover each point on the graph, and it's going to fill all that up. The integral is going to integrate across an infinite number of them between whatever the limits of integration happen to be, or whatever. So you're showing a full size shell here, empty cylinder essentially, but then that's going to get thinner as it fits itself into the graph here. Now this the last disc washer method had a kind of a pi r squared idea where you were using the area of a circle. This one is kind of going to be using a circumference idea and not an area, because that's a hollow shape right there. So we're going to be looking at the outside area of that cylinder. Let me kind of give you an idea of what's happening here. It's a little sketch I have on this other page. I'll come back to that at the end. So, and then obviously I could have done this both ways. I just did it just X for an example. It works both ways. If the thing is, the cylinder would be sideways if it was for y-axis. So you take this thing and pretend like it was just like a sheet of paper rolled up into a cylinder, and it has radius p of x. This book's using p of x. I don't know why they don't use r of x. A lot of books kind of would use r of x, which seems to me to make more sense to represent radius. And then h of x is the height. So imagine if you just took this thing and you rolled it out to a rectangle like this. So the length of this rectangle would be, if the radius is px, using the formula for the circumference of a circle, which is 2 pi r, would make it 2 pi x all the way around that, which would then become that straight line right there on the rectangle. And then these are both the same right here. To the top would both be h of x. Now that gives you an area. So if you multiply the length times the width, you get an area, but we need a volume. So the volume is essentially the thickness of this rectangular sheet, which at this angle you can't see. It's the thickness is, and it's a little better angle right there. The thickness would be, they're right there. Your delta x is whatever thickness that is right there. And then therefore, so then if you have an area and then times a height, that will then give you a volume. So that's how this turns into a volume. All right, let's go back to the notes here. And that's what's going on right here. It's filling up all those. Now this example I'm going to show you on the next page is very, very similar to this idea right here. The function's almost the same, it's slightly different. But this first example I'm going to show you is where we have to use a shell method. We're going to see it throughout here, and many problems could be done just as well with shell or washer. Some are, like the first one I'm going to show you, is kind of mandatory shell. A couple I'm going to show you at the end where it's not mandatory disc washer. It's just those would be probably better and easier methods to use. But a lot of times it's probably not any more difficult one way or the other. But this one clearly justifies why we need the shell method. Okay, so this one's very similar to that picture I have right above this description. Now, there's two reasons why this would not work. Because you look at it, you see it revolving around. There's kind of a shape of it right there with a hollow part in the middle. You're going, hey, couldn't that be... and this is just kind of showing how the cylinders would expand, the shells would expand to fill each little part of the circle, or part of the area volume. Anyway, so you might think, okay, well, why can't we just use the washer method and go outer minus inner kind of, thing, because it does have a gap in there. Well, there's two reasons. Number one is that it's the same graph here. So you need to really have the idea of an outer minus an inner radius. They need to be two separate functions. Well, this is the same function, so there would be no concept of an outer radius minus an inner radius. But even more importantly than that, here's the next part. To use the disc washer method to go around the y-axis, you need to be in terms of variable y. Well, the problem with this equation, y equals 2x squared minus x cubed, and as I mentioned all this right up here, dw, of course, is just short for disc washer. You can't algebraically solve that for x in terms of y. So you'd be stuck. You could not do it by the disc washer method. You could not solve that. But it works perfectly fine using the shell method, filling that thing up with a bunch of cylindrical shells. So to do that is we have these, go back up, you see you have these right here, those two functions multiplied together. So in this case, and your rectangle, which is basically dx, that's the thickness. So your distance out to that rectangle is going to be x. And then, which is p of x here, which, like I said, I mentioned earlier, a lot of books would use r of x there, but to represent radius, but that's okay. And then h of x being the height to the graph, which is the function itself. Okay. All right, so, and then what you do is, and now here, it gives you these intercepts 0 to 2, but I'm just looking at it, suppose it didn't show us that. Our limits of integration for this method are going to be on the x-axis. So I just solved it algebraically. I took that equation, set it equal to 0, and got 0 and 2, which are these 2 points right here. They were kind of given to us in a way, but I just wanted to show you, if they weren't, how we would get that 0 to 2. All right, so we have 2 pi, and there's the formula right here, with the vertical axis 2 pi. So always be careful. I mean, you don't have to memorize formulas in my class, but to look at it, this one, the other method is 1 pi in front. This one has 2 pi. Obviously very, very critical, whether it's 1 pi or 2 pi, or your answer will be twice as large or half as large, and it'll be incorrect. So you take these two functions and multiply together. So there's x times 2x squared minus x cubed, and then your dx. So that's what's making that a volume. And all right, you want to distribute the x before you integrate. You can use the graphing calculator if you want to. That's fine. But I multiplied it, so I get 2x cubed minus x to the fourth. But I'm going to show you how to work this out using antiderivatives. So plus 1, your basic power rule. That would give you 2x to the 4 over 4, which would reduce to 1/2 x to the fourth. And then 4 plus 1 is 5, so it'd be 1/5 x to the fifth. Plug in 2, plug in 0. 1/2 of 16 would be 8. 2 to the fifth is 32. You get minus 32 over 5. And I'm just putting a 5 over 5 over here to kind of show you the common denominator. And so that would make that 40 over 5, which makes the whole inside 8 over 5 times 2 pi. and then minus 0, so you get 16 pi over 5. Now, when I did this in the calculator, I forgot to write the pi here. I have it written down in the next example that I do. But I just, for this, I don't put the pi in there because I want it to give me the answer without the pi, because you can always just tack the pi on at the end. If you put the pi in there, I suspect the calculator would give you some sort of decimal answer. And I didn't want the decimal answer. I wanted the exact answer. But if we just want the decimal answer, that's fine. I just have to know to, put the pi. So you see it gives me 16 over 5. No problem. Just put the pi back in there, and that makes it 16 pi over 5. So that was an excellent example of mandatory use of the shell method. So in this set of problems, where it says anywhere with a 1 through 14, we're going about the y-axis. Okay, so that was the same thing with that last one. We will do the x-axis. Don't worry about that. So here's our function, and then our p of x would be the distance out to the rectangle, which essentially would be x, which is essentially the distance to the edge of the shell at the radius. And then the h of x would be the height. So the height going from 0 to the curve would just be the square root of x. So we have these two functions. And you can clearly see they had to, this one we had to cut it off somewhere because they don't naturally intersect like that last one did. So the graph would just keep going and going and going. So they cut it off at 4. So that tells me my limits of integration are going to be 0 to 4. So the formula is we 2 pi, then we multiply these two things together, x times square root of x. So you just add their exponents. So you have an x and you have an x to the 1/2. Add them together makes x to the 3/2. So 2 pi x to the 3/2 dx. And just real simple power rule here. So 3/2 plus 1 is 5/2. So that makes that 2/5 x to the 5/2 times 2 pi. So that'll give you a 4 pi over 5 x to the 5/2, 4 minus 0. Put in 4. 4 to the 5/2 will be the square root of 4, which is 2, to the 5th, which is 32. Of course, 0 will make that 0. So 32 times 4 pi over 5 gives me 128 pi over 5. Now this one, because it was doable, disc and washer, I just want to show you that as an alternative. So right off the bat, if we're going around the y-axis, which we are, it has to be in terms of variable y. And this function's not too difficult to convert over to y, because you just square both sides, so it gives you x equals y squared. So that's perfect. And then you see going around the y-axis, it's going to leave a washer. It's going to leave a gap in the middle. So the outer function will be 4, and then the inner function will be the curve, which is now y squared. And then the limits of integration will be vertical this time, so they're going to go from 0 to 2. So, and like I mentioned earlier, this formula just has a 1 pi here, not a 2 pi. 0 to 2 vertical, outer radius 4 squared, minus inner radius 4 squared squared. I didn't work out all the math here. I mean, it's not difficult. You could do it easy enough. I just put it in the Maple software. Maple, I can put the pi in there, and Maple will leave pi as part of the answer. So that's yeah. But you can still do it in the calculator, without the pi, and put the pi in there. But look at the answer compared to the one above. So both methods correctly yield the same answer of 128 over 5 times pi. Now this one's number 9 in the same set of problems here. This is, so we're also going around the y-axis. Don't worry, I promise you we're going to do the x-axis. It should be probably the next one after this one. Yeah. So here's this function, y equals 4x minus x squared. And we're bounded by the y-axis, x equals 0. And then the horizontal line, y equals 4. So it's a vertical rectangle because we're going around the y-axis. And then the distance p of x from the axis of revolution to the rectangle would be x. Like so. Now, this is a little tricky. So the h of x needs to be the height inside the shaded region of what's being revolved. You see the last one, the shaded region was going from 0 to the square root of x. So that height would be the square root of x. But here, it's the difference, I should say, between these two curves. That's what h of x would represent. That would be the height at all times here. So it would be actually the outer line, minus the curve, 4x minus x squared. And then it's 0 to 2 on the x-axis. So we would have 2 pi, 0 to 2, and then p of x and h of x just multiplied together. So, here I solved it just algebraically. That goes 0 to 2. That's how you can do it. You just set this equal to 0, so you know exactly where... I'm sorry, you set it equal to 4. I figured out set it equal to 4 to where this is going to cross. We know it's starting at 0 here. That's not the issue. Is where is it hitting right here, that point. So I just set these 4 equal to that. Well, actually, that is setting it equal to 0. And move the 4 over, and you get 2. So that's okay. That's about what we thought it would have been, but that's just a more precise way to solve it. So now you have these two functions multiplied together, and then be careful, of course, when you distribute the negative, it changes both of those signs. Multiply the x through there. Pretty basic antiderivative here. 4x would be 2x squared, minus 4x squared would be minus 4/3 x cubed, and then x cubed would be 1/4 x to the 4th. And you put in 2. 2 times 2 squared is 8. 2 cubed is 8, so that would be minus 32 over 3. And 2 to the 4th is 16. 1/4 of that would be 4. So that makes that 12 minus 32 over 3, which you can easily come up with 4 over 3. So it's 2 pi times 4 over 3, which gives me 8 pi over 3. Here, actually, see, I wrote the pi in. I forgot to write the pi in up there earlier, but so I put it right in here, before I even simplified it, and got the right answer, 8 over 3, and then you put the pi in there. Now, this one shell method, I think, is an advantage because unlike the one I showed earlier where I told you that you could not solve it for y, this one, you can solve it for y, but it's a bit of a nuisance. You got to do kind of a completing the square process. So it is doable, but it would be just by the time you do all that, you can kind of work it out with the shell method and be done. So the difference is it's not mandatory you use the shell method, but it's easier because of having to complete the square and solving for the y. All right. Here comes the x-axis. Y equals x cubed, x equals 0, y equals 8. So there'll be that shaded region right here. All righty. X-axis for the shell method means we are integrating with respect to variable y. So your rectangle goes this way, and that's because the thickness of it is dy on the y-axis. And then, so that vertical distance here is going to be y, and then the distance out to the curve is going to be, which you can say that's basically the height of your shell. Anyway, the shells are actually sideways this time. They're circular shells that might, I don't have a stylus with me, but unlike the other shells, they're kind of going this way now. Let me draw it right here. Like so. And then it goes this way. So I'm kind of freehanding that with a stylus. With a mouse pad. So that's why, yes, that's your H is now going this way. Out to the edge. And then that's your radius is right here. which is the y. Okay, because the shells are now a different shape, different cylindrical shells are not upward, they're sideways. All right. Okay, y, then you just go y times 1/3. The limits of integration will be y also, so it's going from 0 to 8 on the y-axis. So you go 2 pi, 0 to 8, y times 1, y to the 1/3. That's easy, you just add exponents. And so that gives you, add exponents, 1 plus 1/3 gives you 4/3. We use the power rule. So 4/3 plus 1 is 7/3. So it'd be 2 pi times, then you divide that by 7/3, makes it 3 over 7 in front. So 3 over 7 times y to the 7/3, 0 to 8. 2 pi times 3 over 7 is 6 pi over 7. 8 to the 7/3, which the cube root of 8 is 2. 2 to the 7th is 128. So our exact answer would be 768 pi over 7, which is exactly what Maple gives us right over here on the right. And let's look at this one from a disc washer method. This could be doable, the disc washer method. You have going around then the x-axis, it would be outer minus inner, but we're doing this time as a function of x. So this one, yeah, you don't have to, you want that to be y cubed, obviously. So you got y equals 8 on the outer, y equals x cubed on the inner. So it'd be 8 minus x cubed, and it would go from 0 to 2 right here. And you can figure out the 2 real easily by putting in 8 right there for y. If 8 equals x cubed, that means 8x is the cube root of 8, which is 2. So it's going from 0 to 2, outer minus inner, 8 squared minus x cubed squared from 0 to 2 is pi. I didn't work this out. It wouldn't be hard to work it out, but the point of all this, for these, when I show it by the other method, I want you to see the setup, and then if you want to work it out for practice, nothing wrong with that. But I want you to see the setup, and then that the answers match. So this is also giving you 768 over 7 pi. So that one was, I think, pretty doable by either method. Now here's one actually where the shell method, did this one say, this is also the x-axis. It can be done, but it's not the best method. Because we've got the reason why I have two different rectangles here is because this graph up here we've got two different distances here. Until you get to where the curve hits right there on the y-axis, you're going from 0 to the line, all right along here would represent that one rectangle. But as soon as you come up here, it's the blue curve to the line. So it's two separate pieces essentially. So what would have to happen here to use the shell method is you would have to do two shell methods and add those results together, which I've set these up for you. I'll just show them. I'm not going to do all the work on these, but I've got them set up, and I'm going to explain how they're set up. Now the separation point on the y-axis is the square root of 2, because when x equals 0, you plug it right into there, 0 for x, and you're going to get the square root of 2. And then here, for y equals x, it's going to be at 2. You could solve that by putting x in here and do a little algebra, but you can kind of figure it out by if you put 2 in here for x and 2 in here for that x, they would equal each other, right? Because the square root of 4 would equal 2. So that's 2 right here. So you have one shell method from the 0 to the square root of 2, which is that integral. And then you have another one from the square root of 2 to 2, which is right here. Now here, the first one, they're both going to be y's. The height's still going to be y. But the distance out, this one is also going to coincidentally be y, just because the function is y equals x, which is x equals y. So that's the only time that these would both be y, is whenever you're dealing with the line y equals x. But here, you see this one is going to be the outer minus the inner distance. So it's the line minus the curve. And for the curve, you have to solve that for y, which, I mean, for x in terms of y, which is not that difficult. You would just square both sides, and you would have x plus 2 equals y squared, and you move the 2 over, so it's x equals y squared minus 2. So it's outer minus inner, so there's how I got the y squared minus 2. So it's y minus y squared minus 2. And then Maple kind of gave me something mess like this, and which is, and then I kind of able to simplify it for me and combined it and got 10 pi over 3. So now let's see, this one, the washer method, is easier, and of course we've got to make sure it represents the same answer. Now the washer method, so we're going around the x-axis, so visualize it, it's still going around the x-axis, but all we have to think about now is outer minus inner radius as you're going around the x-axis. I'm going to draw this in here and then I'm going to erase it. So now we have essentially a vertical rectangle this time, like so. And we're going outer minus inner. So this is going to be, and then limits of integration for this one also going to be 0 to 2, because that's where it is. It's the same on the y-axis as the x-axis here, 0 to 2, because of y equals x. And then 0 to 2 vertically. So 0 to 2 horizontally, outer minus inner would be the square root of x plus 2 squared minus the x squared, and there's a 0 to 2. So you have x plus 2 minus x squared. Pretty easy to work out from here. Antiderivative of x would be 1/2 x squared. Antiderivative of 2 is 2x. And then minus 1/3 x cubed. Put in 2, put in 0. Pretty basic arithmetic here. You'll get 1/2 of 4, which is 2. 2 times 2 is 4. Minus 8/3. That's going to give you 6, which is 18 over 3, minus 8 over 3, which is 10 over 3. 10 pi over 3. So you see it did produce the same answer as that shell method. So it looks like I did, obviously shell method was a little trickier because of the two pieces and stuff, but you can feel pretty good about for sure what we did using the disc and washer. So yeah, but the fact that my shell method process matched that makes me feel like, all right, then I know I set both of them up correctly. But I was really, the disc washer was pretty confident. And here, this one's similar to the last one in the sense that the disc washer would be much better, because once again, you got these rectangle distances are not the same. So you have to split it up where you got a bottom rectangle and you got a top part. So you got y, the vertical distance is y. Since that's a rectangle, that distance out is going to be fixed value of 1. It's not going to vary. It's going to vary when you get to the curve, but it's fixed here at 1. So this ends up being 1 over y, because y equals 1 over x means x equals 1 over y minus that 1. And this 1 comes from the distance from 1 to 2 is 1. So 1 over y minus 1, and they both have y in front, and you're going vertically 0 to 1/2, 1/2 to 1, 0 to 1/2, 1/2 to 1. I didn't work this out because obviously this is by far the least desirable method to do it. But this is a really nice one if you revolve it around the x-axis. So visualize that shading going around the x-axis. Now this one is not even a washer. It would just be a solid disc, so there would be nothing to subtract. Your limits of integration would be x, 1 to 2. And you have just a single pi in front here. And you just take 1 over x and revolve it around, and it's just 1 over x squared. I didn't work out the integral there, but it wouldn't be difficult. And but just wanted to show that it yield, pi over 2. So both ways yield pi over 2. So, why these last two examples were doable, both methods, I think I'd have to give the edge to the disc washer method. And now here's kind of a little summary here. Then I'm going to go to another page and show you a summary, and we'll be done with this. So it's kind of wrapping up the two methods here, and it's kind of showing you, okay, for the disk, if you're going around the y-axis, your rectangle is going to always be perpendicular. And then, of course, you know, with the disk method, if it's y-axis, we're integrating respect to y. If it's x-axis, the rectangle is vertical, perpendicular to your axis, and you're integrating respect to x. You come over here for the shell. If you're going around the y-axis, your rectangle is parallel to it, like this, but it's variable x, because the width of that's going to be delta x, so it's variable x. And then here, when you're going around the x-axis, your rectangle is parallel to the x-axis, but the width of it would be dy, so it's variable y here. So it's the opposite variables for the shell method. I don't know why I included these two pictures here. It's just kind of showing you. These are showing disks, I guess, and that one's showing a cylindrical shell. But I do have one more thing I want to show you here that I found just kind of in a YouTube video. I can't draw very well, so I want to show that to you. And then this is something you could kind of like in this video, and then just kind of pause it once I'm about to stop here in a second, but you could pause it in the video, and just that way you could look at it more carefully if you wanted to. So this is a graph where it's essentially taking this region here between these two curves and revolving it. So first time it's revolving around the x-axis. So it's going around there. So you see the pictures, they have a washer drawn in there, which is correct, because you'd have an empty part in the middle, an empty part between these two curves. So outer minus inner, so it's a bunch of washers. So washer method, so your thickness of your washer, that's your delta x. We're integrating with respect to x, so it'd be outer radius. So you assume the outer curve would be big R, and the inner curve is little r. So it's r squared, big R squared minus little r squared, and then whatever a to b happens to be. Now the same problem using the shell method. You see the thickness of the shell this way is vertical, dy, versus that one's horizontal for the disk. The thickness is vertical here, dy. So we now have, and they have it simplified basically as, which is fine, 2 pi r times h. The r was what we defined, and this book defined as the p of x, or in this case, p of y, excuse me. P of y for this one would be p of x for the other one, the circumference. But that's what that r is representing. You see there it is. That's what we called p, was that radius. And there's your h, the height of it. Picture if you're looking at it at the other sideways angle, that's your h. And it's going from c to d, vertical limits of integration. Okay? And so here they're basically taking the same graph and rotating it around, same kind of picture, and it's leaving a gap in the middle. So here's the washer. And then when you're going around the y-axis for the disk washer, it's going to be variable y. As you can see, your thickness of the washer is dy. And it's going to be outer minus inner radius with respect to y, though. So whatever these equations are, if they're in terms of x, they have to be converted to y, which we saw with that first example I did in the notes here that might be impossible. Then you'd have to use the shell method. And we're going from c to d vertically. And then the last one then would be the same thing, revolving around the y-axis with the shell method. So that means we're going to be using variable x. And then you see this dx is the thickness of your shell, like so. And then your r, radius, which we called p of x, r of x, right there. So that's basically your 2 pi r. And then here's your height. So that's giving you your area, 2 pi rh. That's the area, and the dx makes it the volume. And they're just kind of drawing a picture here showing you that. You see they've got a cylinder wrapped around these two edges of the graph. So like I said, it's just a bunch of infinite cylinders you would draw touching those lines, until it fills up the entire region, until it covers all of that. A bunch of infinite shells in there. So, well, all right then. That's going to conclude this video on volumes of solids of revolution by the shell method.